Hello everyone, today I am going to try to explain the math behind the possible positions of lab locker. It is only a small grid, but it will explode very fast. So what is lab locker? Lab locker is a 5x5 grid that involves coloured flasks and poison bottles. The top number will show the ticket value. The bottom number will show the number of poison bottles in a column or a row. The player must complete all 3 rounds in order to win the jackpot. The jackpot starts at 1,500 tickets and increases by 10 per fail until the jackpot is won. Along with that, the player can choose to leave or carry on at the end of round 1 and 2. However, the results almost always result in the player carrying on. So now we will go over the constant values that I came across when I played this machine. Round 1 is always going to have 4 yellow flasks and 5 poison bottles. Round 2 will always have 5 blue flasks and 6 poison bottles. However, round 3 is more random. Round 3, or the jackpot round, is different. Instead of ending upon collecting the required flasks on condition, such as 4 yellow flasks on round 1 and 5 blue flasks in round 2, it requires you to collect every single flask in order to win the jackpot. The number of yellow and blue flasks can vary, but what will be certain is that there will be 2 to 4 yellow flasks and 1 to 3 blue flasks. But the amount of poison bottles will always remain at 7 every time you reach the final round. This is the how to play sheet that I found on the machine, which you can find as well. So now we'll go to the hard part, calculations. So I initially thought this was something to do with factorial, so I did 25 times 24 times 23 and so on all the way to 17, or 25p9. For those who don't know, the p is permutations, which is a formula called NPR equals n factorial over n minus r in brackets factorial, where r is the number of ways to arrange objects from a set of n distinct objects where order does matter. However, I made an error. The problem is you can't put an identity on poison bottles because they all function the same. Instead, I will have to use the combinations formula, which is n choose r equals n factorial over r factorial brackets n minus r close brackets factorial, where n is the total number of objects and r being the number of objects we choose. So we do the following for round 1 and round 2. I input 25 choose 5 times 20 choose 4 into my calculator. 257,414,850. You can swap the 4 and 5 around and it will not change the result, but you have to be careful when adjusting it. There is something linked to that, but we will get to that later. Round 2 involves 5 blue flasks and 6 poison bottles. So after I input 25 choose 6 times 19 choose 5 into my calculator, I got 2,059,318,800. However, when it comes to the final round, there's actually more possibilities. There are 9 possibilities that I have to calculate in round 3. While there will be the number of poison bottles is a constant 7, the number of yellow flasks is going to affect the number of empty squares left to the blue flasks, which I was able to transform into the formula 25 choose 7 times 18 choose y times 18 minus y choose b, where Y is the number of yellow flasks and P is the number of blue flasks. So now we will go over the identity. At first I input 25 choose 7 times 18 choose 2 times 16 choose 3. And then I input 25 choose 7 times 18 choose 3 times 15 choose 2. And then both of them gave the output 41,186,376,000. And turns out there is an identity of this. An identity for this. The following identity, n choose A times n minus A choose B, equals n choose B times n minus B choose A, which says when you choose A items and then B items, it will give you the same number of outcomes as choose B items and then A items. So we now made it to the result. After I spent 20 minutes inputting the calculations into Wolfram Alpha, since my handheld FX85GT Casio calculator is not good enough for this, in order to get the exact digits, I multiplied all of the values together. I inputted 257,414,850 times 2,059,318,800 times the round 3 value 966,605,019,600, and I got a really large number. 512 octillion, 993 septillion, 750 sextillion, 640 quintillion, 896 quadrillions, 507 trillion, 125 billion, 928 million. Or just close to 513 octillion. 3 round lab locker games that could exist. And it is insanely large that even if you had a hypothetical computer that can perform 1 septillion of these games per second, it's still going to take you almost 6 days non-stop just to get every single game. Will there be a possible part 2? Well, maybe. But there is a variant called Lab Logger Hardcore, which is absolutely insane. There was a video of it made by the head moderator herself, Boards Open, where she won the jackpot of 74,913 tickets after she successfully beat all 4 rounds. And if there is enough people who want me to make a part 2 to this, then I will do it. And who knows, it will feel like forever doing it, since this one took me around 10 hours to do. But if enough people want me to do the hardcore version, I will do it for you.